All right, so we've talked a little bit about integer programs before and integer variables. So today we're going to use a special variable called a binary variable. And as I talked about earlier, the binary variable is a special variable that can take on only two values, and hence it's binary, 1 or 0. So today we'll get to the point where we can define these variables and write out formulations using them. So So I'm going to look at three different general ways of using binary variables first, and then we'll apply those general ways in different problems. Okay? So the first way is where we try to model the condition where we want to choose some subset of items. So in this case, we want to choose k out of n warehouses. If you recall, we did a problem like that. We want to choose 15 out of 60 warehouses. So say we have 4 warehouses and we want to choose one location. So the way to define the decision variables is we always set the decision variables in a particular structure. I always like to use y because then it stands out as a binary variable in any formulation. You often see different people using different variables. Sometimes they use Greek symbols. I like to use x and y. So the way we define the structure of the variable is whatever variable, in this case yi or y1 is equal to 1. So it's true. 1 is often indicates true. So y1 is equal to 1 if we locate in Georgia. So what is the condition if that statement is true? We locate in Georgia. Then it's true. 0 otherwise, it's false otherwise, or it does not take on any value otherwise. So that's the general structure of defining any decision variable that is binary. So we're always going to follow this structure. The decision variable is equal to 1, and the condition that makes it true, 0 otherwise. So this simply means otherwise. So the constraint is very straightforward. We take the sum of these binary variables because what is each value? Either 1 or 0, right? So it can be either 1 or 0. So by setting it equal to 1, what we are doing is we are forcing only one warehouse to be open. Now, what if we could choose at most 2 locations? How would we formulate that condition? Okay, so we say the sum of all yi's from 1 to 4 is equal to 2. Is that right? Everybody does not look sure, so. Less than or equal to 2. Is that right? So the key thing is at most, right? But in this case, we could also say that 0 was chosen, right? Is that what we want? No, we don't want 0 warehouses. So how do we ensure it's not 0?
Would you have 2 then? 1 less than or equal to 2 and greater than 1?
So it's never greater than or less than. It always has to be greater than or equal to or less than or equal to.
Okay.
Right. So you remember those rules? It's always either greater than equal to, or less than equal to. Because what would greater than equal to mean is that you're constraining it to be equal to 2 only, right? Because it has to be an integer. So at most 2 means it could either take on a value of 1 or 2. Yeah? So when you do practice problem 4 in the practice set 1, you'll be able to use this kind of a constraint. Okay. So the next one, everybody understand this, right? So the next one is where we can model fixed costs. So we incur a fixed cost only if we open a facility or if we locate a facility in a certain area, okay? So in this case, we say we locate a facility in Idaho only if we have a fixed, we incur a fixed cost of $300,000 only if we locate a facility in Idaho. So what we do is we define a decision variable, y4 is equal to 1 if we locate in Idaho, and y4 is equal to 0. So this is just another way of structuring it. So we have our usual variable costs. So say this is a transportation problem. We have our transportation costs, right? All the lanes times the cost of transporting on those lanes. And then what we have is the fixed cost multiplied by the binary variable. That's added to the objective function. It's pretty straightforward, right? Okay. The final way is this is what is really powerful about binary variables is we can model dependent decisions. So all kinds of logic we can define. So just like we've been solving these various logic problems, we can think creatively and add all kinds of nuances, and we'll see some of those versions a little bit later on after we do some examples. So now we are saying that we locate in Idaho, we have a binary variable. And also the number of units we ship out of Idaho, that's a continuous variable. So in this case, we have the model of a dependent decision. So the dependent decision is modeled using this constraint here. So here we have the amount that we can ship out of Idaho. So it's actual shipping quantity. This is the capacity of the warehouse. And this is either 1 or 0. So here you can see that if the binary variable is 1, in other words, the condition that we locate in Idaho is true, then the right-hand side is going to take on the value C, which is the capacity of the warehouse, right? So then we can ship, X4 can take on any value up to the total capacity of the warehouse. Yep? But if it's 0, then X4 is forced to be 0. In other words, we cannot ship out of the warehouse. So here we are dependent upon whether the warehouse is open or not. If it's open, we can ship. If not, we can't. Right? So that's how we model that decision. Okay? All right, so let's do an example now. So look at your slick oil problem next. Straightforward transportation problem. We have 3 warehouses, 3 customers, and we have transportation costs for relay. We've done this a number of times. Your homework has it. Practice problem in class, we've done it, right? So now what we do is we add some nuance. We incur a fixed cost of $100,000 every time we open that particular warehouse. So obviously we have to add a binary variable, as we just saw. So I'm going to define the binary variable yi is equal to 1 if we use warehouse I and 0 otherwise. Then we add our forcing constraints, our dependent demand constraints, right? Where we ship out of the warehouse only if that warehouse is open, right? We just looked at those dependent constraints. So we have our objective function, fixed cost elements, and then we have these dependent demand constraints. So if you look at the right-hand side of each row, they're all the same. So that tells us that we can actually combine those three constraints on each row to make one constraint, right? Because what we could say is the amount we ship out of warehouse 1 has to be less than or equal to 500 times y1, right? Now I'm using 500 as a large number as the sum of the total customer demand, because clearly we cannot ship out more than what the customer demands, right? So we can also use a large number, and the reason why we use a large number is, think about it, if we have 100,000 customers, we're not going to go in and write out every single 100,000 every one of those 100,000 customers demand on the right hand side, the warehouses on the right hand side, right? We're going to just use some large number. Maybe we could use the sum of all the customers. We could just use some arbitrary large number, right? And that's what we're doing here. We're just using some large number. In this case, it happens to be the sum of all customer demands. So we could combine each of these rows into a single constraint, like this. So all we are saying is the amount we ship out of each warehouse is less than or equal to the total demand if that warehouse is open. Now the reason why the 500 does not matter is because I've already got warehouse capacity constraints over here. So those warehouse capacity constraints will actually restrict the amount that is actually shipped out of each warehouse. But then again, that gives me a clue that says the only thing different between this constraint and this constraint is the right hand side. Yep? The only thing different between this constraint and this constraint is again the right hand side. So I can combine it further and I just have one set of constraints, the capacity constraints, and I just multiply the right hand side by the binary variables, right? y1, y2, y3. So do you see that? So basically we have the same formulation as before. All we're doing is we're just simply multiplying the right hand side value by the respective yi binary variable. Because now what we're doing is we're saying that only if that warehouse is open can we ship out of that warehouse up to the total capacity of that warehouse. Yeah? Is everybody with me so far? Because now we're going to take it up a notch. So now we're going to model what's called a single source constraint. So in supply chain and in logistics, it's often, you often want to do business only with one supplier. So you want to find out from a total cost perspective, which is the cheapest supplier. Cost of product, cost of transportation, total landed cost, right? So here we have a small problem. We have 3 warehouses, 3 retailers, and we want to model each customer being served by only one warehouse. Okay? So what's the first step that we do? What's the first step? Obviously we want to follow the same steps as before. We have the 4 steps. First is define the decision variable, right? So what's the decision variable that we define? So just to give you some help over here, let's think about the problem as it stands. So we have warehouse 1, warehouse 2, warehouse 3, right? Customer 1, or let me use colors over here so it becomes a little bit easier. Customer 1, and so we have customer 2, and then customer 3. So if you look at each set of colored lines, there's only one that's going to be selected to serve that customer, right? So how do we define our decision variables? So now you're talking about the solution. And that's what the mathematical program will do, right? So in a small problem, we can clearly eyeball it. But if it's a large problem, we have 200 customers, we have 60 warehouses, it's going to be impossible to make that determination. So how do we set up the formulation so that the math problem will tell us how that is done? So the first step is defining the decision variable. So the decision that we have to make is what? Which warehouse will serve which customer, right? So now we have these 3 sets of lines, 3 colored sets of lines, and each of these sets of lines represents 3 ways for a customer to be served by the warehouses. So only one of each colored set will be used, right? So how we define our decision variable? So we want to do, so our decision is so remember the decision is usually how, why, what, when. In this case it's which warehouse serves which customer. So just by writing that out, that gives us a clue of how we can define our decision variable. So how do we define our decision variable? So remember it has to be y, right? It's a binary variable. So y. So then how do we proceed from here? And we know it has to have some subscript, has to have an equal, has to have a equal to 1, has to have a 0. So what's the condition if it's true? And what's the condition And of course, the contrary condition will be 0, right? So what's the condition that should be true? That's the statement that we're looking for. That's why we did all those logic problems. Okay? Okay, so you're on the right path? Yeah?
So it would be yi equals 1 if we're using warehouse I.
We use warehouse I to do what? Remember? Now the subscript you mean. Yeah? So Yij is equal to 1 if warehouse I serves customer J. Right? Does that make sense? So remember, the reason I drew this diagram in the first place is this is the diagram that gives us a clue as to how we're going to define the variables. Because this is the diagram they drew when we defined the variables as Si, S11, S12, S13, right? To define warehouse, the amount we ship from warehouse 1 to customer J, or warehouse 2 to customer J. So in this case, we would use a very similar construct, because what are we doing now? We're trying to block lanes, right? We're going to shut off lanes. So the same construct that we use for shipping, we're using for blocking, because the construct is based on lanes, right? So again, when you have to define decision variables in your practice, then you're going to think of the construct that you're using, right? What is it that you're trying? You have this subset of items, and these subset of items are defined in this particular way. So I'm going to have to define my binary variable in the same way using the same subscripts, right? This product coming from this plant going to this customer, right? Or this truck of this capacity of this service, TL, LTL, freeway double, 16-wheeler, etc. So whatever that construct is that you're trying to restrict, you go back to the original construct that it represents. Good. So we define our decision variables. Yij equal to 1 if warehouse I serves customer J and 0 otherwise. So now how do we add constraints? Again, going back to our diagram, we get a little bit of a clue, right? We have 3 sets of arrows, and of those 3 sets of arrows, only one can serve that customer. All right, go ahead.
This just be each warehouse going to one customer equals 1.
Yeah. So for example, this one would be Y11, right? This one would be y21, right? This one would be y31. Yeah? This one would be y12, y13, y22, y23, and so on. So how would we say that? y11 plus y21 plus y31 is equal to 1, right? So, we've now defined our lane constraints, our single source constraints. Now, what happens with the single source constraints? It's turning off two of those lanes, right? So, if a lane is shut down, we also have to make sure that we are not shipping anything on that lane, that the math program is not putting any values on those variables that represent those lanes, right? So, we have to now shut down those lanes using these forcing constraints. So for example, if we were at lane 2-3, the amount we're shipping out of on lane 2-3 has to be less than or equal to 500 times the binary variable for 2-3. So this ij just says that the same I on the left hand side, or the left hand side I is the same as the right hand side I, okay? So that I and j, they represent the same number on both sides. So for all I goes from 1 to 3 and j from 1 to 3. So in other words, we'll have 9 of these forcing constraints because there are totally 9 lanes. So again, 500 is the number of the total customer demand.
Okay.
So it's just a large number. I could put in 2,000. I could put in 1 million. It doesn't matter. Because these SIJs, they're going to be restricted by the capacity constraints and the customer demand constraints. So everybody's with me so far? All right, because now you have to do the next one yourself. Okay? So, it's a modification of the production inventory problem. So again, define the decision variable, write out the objective, write out the constraints, and the restrictions. So how do we define the decision variables? So what's the decision we have to make here? Okay, so we defined that last Thursday. Remember, it was P1 is the number of gallons to make. But here we incur a fixed cost of $50 we produce in a week. So now what is the decision that we have to make? Whether or not to produce, right? So how do we define a decision variable? So remember, 1 is the condition if it's true. So what's the true condition here? So clearly it's y something is 1, and the condition that it is true, that it is 1.
So if you produce during week 1, it equals 1,
Yeah, so y1 or yi, let's use y1, is equal to 1 if we produce in week 1. And 0 otherwise. Y2 is equal to 1 if we produce in week 2, 0 otherwise. And y3 is equal to 1 if we produce in week 3, 0 otherwise.
Why do you only use 3?
Sorry?
Why are we only using 3?
Because I think there are 3 weeks, right? From the original problem, didn't we have 3 weeks? From last Thursday. It was the production inventory problem. Yeah, the whole book has got 4 months.
Okay.
So the objective has, I've already added the decision variables to the objective, so it's just 50 times y1 plus 50 times y2 plus 50 times y3, that is the fixed cost. Now, we have the 3 constraints that define the inventory, and we also have the production to satisfy demand. So we also need to add some forcing constraints. So what are the forcing constraints that we need to add to this problem here? So if we produce in a week, then that results in that week decision variable taking on some value, right? So if we produce in week I, if yi is equal to 1, then pi is going to take on some value, right? Some real value other than 0. But if we don't produce in that week, we don't produce in week I, if yi is equal to 0, then pi has to be equal to 0, right? So there's that dependent decision that we need to model. So how do we model that dependent decision? The constraint, we've already seen how to do that, so how do we write that down? So I'm just going to take the sum of these, because that's the most I can produce in a week, right? 600. So now if I produce in a week, if I have a setup cost incurred in that week that I'm going to set up to produce, only then will I produce in that week. So I'm sure some of you are asking yourselves, what about the inventory? Why is the I sub I not affected? So we also have inventory decision variables, right? The I sub 1, I sub 2, I sub 3, the amount of inventory we have at the end of that week. So why is that not affected by the dependent decisions? Yeah?
This is just like a production problem, so inventory isn't taken into effect because it's already planned for.
Inventory is going to be
There
a.
kind of thing.
So inventory won't be planned for in this particular problem. Inventory is going to be a result of the production, right? Because the way we formulated these constraints, remember we formulated the constraints as the amount of inventory I have at the end of week 1 is equal to how much I produce in week 1 minus the demand of week 1, right? And the amount of inventory I have at the end of week 2 is the amount I produce in week 2 plus the inventory from week 1 minus the demand of week 2. So inventory is just a result of the production, right? So that's why it's not affected by the dependent decision. Only production is affected by the dependent decision. Inventory is just a result. That's how we define inventory. Yeah? And then we have the variable restrictions, y1, y2, y3, and you can write it as a set of, or the defined set of all, in this case, binary 0, 1 values. Any questions? This will be on the exam.
A binary?
Possibly. Actually, will be.
Are there going to be more than one? Is it
It'll be one problem that has about 5 or 6 parts, which you'll have to write out. There's no multiple choice.
Is there going to be any optimization like on the computer?
Would you like some? No?
No.
I could arrange for it. You're giving me ideas now. I'm pulling a leg, Michaela. Alrighty. So the beauty of binary variables, hopefully one day you will be able to behold the power of these binary variables, is the fact that they can do a lot of really nuanced features in models, and they can do a variety of different things. They can set up schedules, they can set up shifts, they can do optimization or help with optimization of some really abstract concepts, and we're going to look at some of those in a second. So one of the things I was talking about shifts is, say for example you have receiving or you have shipments in a particular week, and you can only ship a certain amount, right? So anywhere between 20,000 and 40,000. So you can only ship that much. So say you'll have shipments coming in, and you can only ship to the customer if it is a minimum of 20,000, and you cannot ship more than 40,000. But what if you have to do that at a particular day of the week, or your variable or your program is set up that you can only do that if you hit this amount, and you have to select the day of the week. So that's where we can actually set up a binary variable to say for day 1, y1 is equal to 1 if we ship on that day, y2 is equal to 1 if we ship on day 2, y3 and so on, yi is equal to 1 if we ship on day I. So we can combine those two to actually now model the capacity or the amount that we can ship, as well as which day of the week or what shift that we have. So we could also serialize all the shifts in a week from 1 to maybe 28, or from 1 to 60. So all of the shifts in a week we could serialize, and we could say, okay, in which shift, and define specific capacities for every shift. Because now if we use a night shift, then the cost is going to be different, right? If we do use a day shift, the cost is going to be different. So now all we have to do is by simply adding in this case, the day binary variable to each side of that capacity, we can restrict on which day of the week we ship out of that particular warehouse. Then we have something called the knapsack problem. So the knapsack problem was developed in the early 60s. One of the first problems that were developed using linear programming. It's what we call a classic set of classic problems. So the knapsack problem, the reason it gets its name is you have a backpacker and he or she has a set of items. Okay, and they can only take a subset of all those items. They need them for survival, for traveling, for comfort, etc. And each of those items have a certain utility. So clearly survival items have a high utility, luxury items have lower utility. And each of those items have a volume and a weight, right? The backpack only has a certain capacity, right, of volume and weight. And now you have to maximize utility of the backpack, right? And decide which items will fit in that backpack with maximum utility. You can also use that same principle to load trucks, where you have, say, a number of pallets or a number of boxes or a number of packages. Each of those pallets or boxes or packages has a dimension, has a weight, and has a value associated with it, right? Some revenue or margins on that. So now you can maximize your revenue or your margins or your profits by optimizing and selecting which packages go on the truck. If you think of this large warehouse, put yourself in this large warehouse, now you can see for multiple shipments a day how you can now organize the maximization of utilization of those trucks. Now, the knapsack problem can also be used. So think about, everybody's been to IKEA, right? Or you've heard of IKEA. So in IKEA, you go into the catalog and you get a 3-digit location code. The 3-digit location code tells you in this aisle, this rack, this bin, right? So how do you know, if you think of a warehouse, how do you know? You've seen those robotic warehouse videos that we showed you, like last fall. So how do you know where to stack those? How do we plan where do we stack what? If you think about each bin, it's just a 3-dimensional space like a truck. So if you try to optimize, if you have all of these items and try to optimize them, next semester, for example, we're going to look at WMS systems. What we see is for the WMS system, every single item has to be measured. You put it onto this scanner, lasers get the length, width, and breadth, and then you take the weight. So now you take all of these items, you put it into this large-scale optimization, WMS optimization, and it'll find you the exact location for all of these things to be at. Of course, there are other business rules, as in, if somebody's going to order, for example, if you're talking about say an online retailer like Target, if somebody's going to order diapers, they're also probably going to order baby formula, or they're going to also order other baby-related items, right? So they're all going to be in the same vicinity or in the same picking zone. So there's business rules, but there's also these other rules, which is how do we actually locate these packages on these shelves? Now, Amazon uses really advanced algorithms, because now you can find all kinds of items that it's what they call organized chaos. They have fixed bins, fixed shelving, but every single item, there is no logic as to how is, because when somebody goes in, they could buy a book, they could buy a flashlight, they could buy some sports gear, and they could buy a scope for a hunting rifle, for example, right? There is no logic to that, right? But Amazon has studied all these patterns and has optimized how they want to arrange them to maximize the efficiency of the pickers. How do they do that? A large-scale problem set up similarly using binary variables, very similar in structure to a knapsack problem, right? So those business rules now can be incorporated in the different constraints, that if you're going to do this, then you have to have this and this and this also in as well. Does it make sense? So you can do some really powerful things with binary variables. All right, so just take this down, and I think it's better to actually demonstrate how this is used in an actual Excel spreadsheet. All right, so let me just sit over here so I can see the screen. So one of the reasons why I use the simplest formulation is that if I had to use the original formulation for the slick oil problem, the first formulation, I would have to have 9 additional constraints that I would have to list over here. So I'd have to add 9 additional rows over here, right? And that would be really cumbersome. So that's why simplifying the formulation and combining it along with the original formulation was the best way to go. So now the original formulation looked like this, where I had the 3 warehouses, 3 customers, and I had the original S11, S12, S3. Right? This is the original. This is what we're used to, the transportation problem. Then we have the right-hand side, 50, 27, 275, 275 for the warehouses. And then we have the objective function and the variable cells. Now, when we add the binary variables, all we're doing is we're adding 3 more columns for the binary variables. That's all. Now, if we had to do the single source constraints, then we'd have to add 3 plus the 9 more single source constraint decision variables, right? The y11, y12, y13, so on, right? So we'd have to add 9 more columns. In addition, we'd have to add those 3 constraints for the single source, as well as the 9 forcing constraints. So we have to add 12 more rows of constraints, right? So just keep that in mind. But the structure remains exactly the same. So just to show you, okay, so I'm just going to erase this here. So the sum product is the same. Now remember, the sum product also includes the binary variables. The structure of the tableau does not change. The structure of everything stays the same. And we have the objective coefficients. And for each constraint, we also have the sum product. Now the 50, the 275, and the 275 on the right-hand side for the original problem. So why is it here on the left-hand side? So the reason it is here on the left-hand side is just like I pointed out here, when you have x1 less than or equal to 20y1, we just subtract 20y1 from both sides. So in this case, we're subtracting 50y1 from both sides. So our constraint becomes s11 plus s12 plus s13 minus 50y11. Minus 50y1 is less than or equal to 0. right? So remember I said we cannot have decision variables on the right hand side. So all the decision variables on the left hand side. So now the coefficient becomes minus 50. In the same way, this coefficient is minus 275 and this coefficient is minus 275. Is that clear? The sum product is the same. We have the same number of, just all of the cells in that row have to be multiplied by all the decision variables. And we do that all the way down for all the constraints. And then we have this minimize to remind us. And then to set up the solver. Our objective is pointing to this cell here, which is our objective coefficient. We are minimizing. Our changing cells are all of these changing cells. Oops. And the only difference is, for binary, the only difference is, besides of course how we structure the tableau, is we have to set these 3 changing cells equal to binary by selecting this option here. That's all we have to do. Of course, if we had more binary variables, all of the binary variables in our changing cells would have to be selected, right? These constraints are there, and then these constraints are there as well. I've just put them in together. And then once everything is set up, I hit solve. And then you'll see a curious thing. Does it take on values of 1 or 0? Okay, so the problem with that is, sometimes what happens, so here I'll say let's restore original values. So sometimes what happens by default in your options, oops. I don't know why this is not working. Okay. By default, you see that this is checkbox over here. It says ignore integer constraints. So sometimes if you don't get the right integer values in your solved problem, you might go into options and check whether this was selected by default. So just click on that to deselect it and then solve again. And you'll see that now the binary variables take on the true values. And you can see that the optimized solution is given. We only use warehouse 2 and warehouse 3. And it makes sense because warehouse 2 and warehouse 3 together have sufficient capacity to satisfy all demand, right? If we did only warehouse 1 and 2 or warehouse 1 and 3, then you wouldn't have sufficient capacity, right? So very straightforward to set it up in Solver. Any questions? Yeah.
When you're using that solver, like the very last one that pops up, we used to have the simplicity or simplify or something, and I'll get choose 2, 2 or 3, because I highlight them and then you press OK and then it would solve for the other ones. You not do that for binary ones because usually they're code files.
I'm sorry, I'm not following.
Like whenever you press solver, whenever you press solve,
Yeah.
there's a window that pops up, and then you press there were a couple things on the right that we goes to
Answer and sensitivity report, yeah.
So do you know how to press this for binary?
So you won't get those reports. So let me just resolve this and you can see. So for example, if I try to solve this, you'll see it only gives me an answer report.
Okay.
You're not going to get a sensitivity report for binary or integer variables. Any integer variables, whether the binary or not. Okay? So there's ways in which you can get sensitivity reports, because really what you have to do is you have to solve it as an unconstrained problem first, and then solve it as a constraint problem. So putting an integer value is constraining the problem because you are forcing the decision to be on a certain value. Right? If it's unconstrained, then it can take on any value. It doesn't have to take on integer values. It can take on values in between values. So there's some nuances to that. We're not going to get into. If you do a guided program and actually learn how to do sensitive reports for it. Good. Any other questions? All right. So that's it for me. I will see you on Tuesday when we will start simulation.